for this. Okay. Good. I realized last day was our part 2 of the review because we had that review last Wednesday. Quick overview. So today's part 3. Lucky you guys. 3-day review. Yikes. So our final is on Monday morning. First exam slot. Do you get a prize for that or what? Well, the prize is you're done early. But also, I don't know, I think it's kind of cool. It might be my first ever, like very first exam time slot. I'm excited about it. For office hours, so not really office hours, when I'll be at the school, I'll be here, well, the rest of today, because I teach tonight, and then tomorrow and Friday and Saturday, but then my sister is coming into town, so I won't be here on Sunday. Okay? So we'll call them office hours. All day, which I would say is just kind of 9 to 5-ish. Usually I'm here outside of that window as well, but kind of guaranteed 9 to 5 attendance is Thursday, Friday, and Saturday. Okay. You can always text me. 250-864-8386. Preferably with questions. But if you want to just say hi, that's fine too. So you can text me. Calling's kind of weird, so just text, okay? Be normal. One thing that I did want to note was that I kept the tree diagram as it is. So, but what I'm going to do is I'm going to give you what it will look like. Okay, so on the final, the tree diagram will look like, it's going to have 3 branches at the top. So not that huge, massive one that we looked at for the practice test, right? But that was a good one to kind of get into, right? See something a little bit bigger. So it's going to have 3 options as your first kind of phase, and then 2 options after that. Okay. Kind of a classic scenario is you have to pick a door, a red door, a blue door, and a yellow door. And then behind each door, there's a probability of winning, right? You either win or you lose, win or you lose, win or you lose, right? And so each door has some probability, and then the probability of winning has, well, some probability, right? So that's what it's going to look like. I won't give you any more, but now you know, and that's your reward for showing up on the last day.
For that one, for that example, it would be like winning, losing, or winning.
Yeah, so here it would be like, okay, so you've got so people have a choice of 3 doors. The probability that they choose a red door is 0.5, blue door is 0.2, green door is what, 0.3. And then the probability of winning if they pick this door is something. And then the probability of losing after this door is this. And then so each of these will be winning, losing, winning, losing. That kind of thing. So, okay. So that's good to know. Right? So it won't be as bad as the practice test that we went through, right? But it will be 3 branches at the top and then 2 branches after that. Yeah.
Every level,
yeah. Okay. Yeah. So the total probability here be 1. The total probability here, right, for each set of branches. So here's a total probability of 1, total probability of 1, total probability of 1. And then once you find each of these probabilities, they have to add to 1. Any other questions about that one? Pretty good. Okay. All right. So I think, or I know because I scrolled back, we were working on question 4 of the practice final, where we had this normal distribution with a mean of 9.8. Yeah.
Sorry, did you say all
okay.
of these add to 1 or just like each?
Oh, here. So these have to add to 1, add to 1, add to 1, add to 1, but then these all add to 1. That makes sense.
Yeah.
So it's like each bar adds to 1. I don't know how else to show that. But like this. That doesn't make sense. No, hopefully it makes sense. If not, then we can clarify it later. Okay, so we did part A, we did part B last day, so we're gonna jump in and do part C here. And I know it's kind of jolting into it here, but got a lot to get through. Not that much time. So practice final number 1 continued. Question number 4. C. I guess I could bring in the actual blurb. So part A, we had to find some probability of some individual observation, right? A single observation. And then we were given a probability and we had to work our way backwards to find, okay, well, what's the cutoff for that probability, right? So working back and forth. And then now in part C, now you have a sample size of 30 customers. So if 30 customers are selected at random, what's the probability that the average time spent by these 30 individuals will be between 5 and 10 minutes? Include a diagram. So we'll start with our diagram, mostly because it helps us figure out what it is we need to do. And so we've got a normal distribution with a mean of 9.8 and a standard deviation of 3.7. So we want to know the probability of being between 5 and 10. So the probability, remember, is the area under the curve. And so we're looking for this area here. That means we have to calculate a z-score for 5 and a z-score for 10. We have to find the area that we've highlighted here, right? There's lots of ways that we could do it, keeping in mind the total area has to be 1. You could find the area in the tail and subtract those 2 areas from 1. What I like to do and what I'll always do is I find the area to the left of 10, and then I find the area to the left of 5. And then I take this big area and subtract this little area, and then I'm left with the area that I want. Right? So that's how I will always find the area between 2 points. Right? But whichever way you do it, as long as it makes sense what you're doing, you should get the same area. Okay? So we have to calculate a z-score for 5 and 10, right? So just to indicate which one's which, I'm gonna just do a little subscript 5. Is x bar minus mu over sigma over root n, right? Because we're talking about the average time spent. So we're talking about the mean. So now we have 5 minus 9.8 divided by 3.7 divided by the square root of 30. Negative 4.8, and then I'm going to find 3.7 divided by the square root of 30 is 0.6755244488, which I'll store just for later. 4.8 negative divided by that guy, negative 7.105589935. Z, it always has to have 2 decimal places. In this case, because we're so far into the tail, it doesn't really matter, right? But just for consistency, I'm just going to round it to 2 decimal places, negative 7.11. What's that saying? It's saying that this 5 cutoff is actually way out in the lower tail. Right, so it doesn't look like this. This was just to figure out what was going on, right? And so what we can say, and what we know because we've had practice with this, is we can say, okay, well then this area is approximately 0. Because you'll go to the table, you'll find that the smallest value on there is negative 3.49. So negative 3.49 has an area in the tail of 0.0002. So now, because we're so far beyond negative 3.49, we can just say it's approximately 0. So now we're going to calculate the z-score for 10 minutes. 10 minus 9.8 divided by 3.7 divided by the square root of 30. 0.2 divided by 0.6755244488. 0.296066247. Rounding to 2 decimal places, I get 0.30. If we use the Z table, we've got a positive value of Z. That's the positive side. And just to jot it down here, I'll put it on this graph. And then I'll write my blurb later. So 0.30, the area to the left is 0.6179. So just so we know where we're headed, right? If this area is 0.6179, and then we're subtracting approximately 0, the area between here is approximately 0.6179. That area, the little tail end that we're lobbing off, is approximately 0. Okay. So we write our little blurb. So using the Z table, we find the area to the left of Z equal to negative 7.11 is approximately 0. And to the left of Z equal to 0.30 is 0.6179. So the area between Z equal to negative 7.11 and Z equal to 0.30 is approximately 0.6179 minus 0.6179. If you wanted to write the blurb, right, the question was, what's the probability that the average time spent by these 30 individuals will be between 5 and 10 minutes? But in the interest of saving time, I don't think that you should, unless you have time later, you can go back and write your little concluding statements. But once you've got this number, you're done for this question, right? So your little statement after is extra. It's good practice, but I know you might be pressed for time on the final, so you don't have to. It's not something I'm looking for. Any questions about that one? Well, you can always use the probability notation as long as you use it properly. Any other questions? Okay. Then let's keep going. So question 5, 6, and 7, right, from our outline, we said, okay, well, they're going to be a means question. There's 4 different means questions that we could have, right? So of course, there's only going to be 3 in here, and each of them is either going to be a confidence interval or a hypothesis test, right? So you have to be ready for all of those, but there's only kind of 3 questions from the means. So question 5. The time and number of days until maturity of a certain variety of tomato plant is normally distributed with a mean mu and a standard deviation of sigma equal to 3.1. I select a simple random sample of 25 plants of this variety and measure the time until maturity. The sample yields a sample mean of 65.8. And then part A says find a 95% confidence interval for the mean time until maturity for all such tomato plants. And then just briefly going back to part B, just to have a look, make the connection. And so we're going to use the confidence interval to do a quick hypothesis test. So it's not a full-blown hypothesis test, right? But we're just going to use our confidence interval. And then part C, if we want to change our margin of error to be 0.5, what sample size do we need? So it's a sample size calculation. Okay. So here, we have to do a confidence interval. And so we need to know what type of question we have, right? So as soon as you figure you need a hypothesis test or a confidence interval, it's a good idea to figure out what type of question you have, right? Because that'll narrow things down. So you only have one sample, right? So the sample yields 65.8 as its average, right? And so you took a sample of 25. And so you've got a 1 sample mean. And because we're told that sigma is 3.1, sigma is known. Sigma known. Yeah. 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 For the sample size? Yeah. Mm-hmm. Yeah. If it's a 1 sample, we do sample size calculations for 1 sample proportions as well, right? So I think that's the one that you're thinking of. But yeah, this is the only formula for sample size calculations. So pretty good check-in point, right? Does it follow up and get you to calculate a sample size? And is it a means question? Then it's probably sigma known. Right? Okay, so the information is listed here, right? We've got X bar is 65.8, sigma is 3.1, and then N is 25. It's the only one that's hidden. So for a confidence interval for one sample mean sigma known, we've got X bar plus minus Z star times sigma over root N. We know X bar, we know sigma, and we know N. The only one that's missing is our Z star, right? So Z star, and we want a 95% confidence interval. Remember for your Z star, because we use them for proportions as well, we just use the T table, and the Z star is at the bottom row, or bottom-ish row. And so Z star is 1.960 for a 95% confidence interval. So X bar plus minus Z star times sigma over root N. Now we can fill in these values. Here, 65.8 plus minus 1.960 times sigma, which was 3.1, divided by the square root of 25. I'll show my work briefly here. So 65.8 plus minus 1.96, 1.2152. On the final, I don't want you to round any values until the very end, right? And I've gone through and kind of told you, if it's important, told you what you can round to and when. So here, I'll store this. 65.8 minus 1.2152. So our margin of error, right, that's the 1.2152, bless you. 64.5848 up to 65.8 plus the margin of error, 67.0152. Doing the calculations only half the work, right? And so only half the marks, because now you have to interpret this interval. Our interpretation, now that we've built so many confidence intervals, right, the interpretation is always the same. We are some percentage confident that this interval captures, and then whatever I asked you to make an interval of. Okay. So we are 95% confident the interval from 64.5848 to 67.0152 captures the interval we wanted was the mean time until maturity for all such tomato plants. I know that for all what tomato plants, it doesn't matter. We'll just copy the blurb, right? So whatever the blurb says, you don't have to adjust it or anything. Captures the mean time until maturity for all such tomato plants. Nice. Let's go on to part B. So now we wish to see if the average number of days until maturity is 65. Use your 95% confidence interval to quickly determine if the average number of days until maturity is different, of course, statistically speaking, than 65. Okay. Clearly state the null and alternative hypothesis, your conclusion, and why you made that conclusion. And so what we do, if we're going to use our confidence interval for a hypothesis test, all we do is we say, well, is 65 inside this interval? Yes, it is, right? And so we're 95% confident that that is an option for the true population mean, right? Which means we don't have enough evidence to reject H naught, right? And so if the hypothesized value is inside the interval, you don't have enough evidence to reject H naught because it's one of the possible values, right? Whereas if your interval was off of the hypothesized value, then you can reject the null hypothesis. And so our null hypothesis for one sample mean, sigma known or sigma unknown, it doesn't matter, is going to be that mu is equal to 65, right? Your null hypothesis is that mu equals the value you want to compare your sample mean to. And your HA is that mu. We just want to know if it's different. So not equal to 65. When we're using a confidence interval for a hypothesis test, we're always doing a two-sided test, right? Because the confidence interval starts in the middle and then it goes out. And so there's always area in both tails, right? And so that's why for using a confidence interval, we use a two-sided test, or it is a two-sided test. So what we say is that since the hypothesized mu equal to 65 is in the interval, we do not have enough evidence to reject H naught. Therefore, and I'm just rewording the question as an answer, therefore the average number of days until maturity is not different from 65. Not significantly different, I guess. Any questions about that one? That part. Let's do the sample size calculation. If the margin of error was to be reduced to 0.5 in the 95% confidence interval, what size sample would be needed? And so what we know from earlier, right, is when our sample size was 25, our margin of error was 1.2152, right? Now we want to bring that margin of error down, way down to 0.5. So then what sample size do we need? You can derive it just from your confidence interval, right? Margin of error, force it to be 0.5 and then solve for n, or you can use the n formula on your formula sheet. So n is z star, can't quickly do it, is times sigma, I want to say, over m squared. Yeah. So our z star stays the same, right? 1.96. Sigma is still 3.1. M is the margin of error. And so here we've got m is 0.5. And then we can solve for n. So here we've got 1.960 times 3.1 over 0.5 and then squared. 1.96 times 3.1 divided by 0.5, and then square that. I get an N of 147.671104. Remembering for your sample size calculations, right, regardless of what the decimal is, you always have to round up to the next whole value, right? And so because we can't take 0.67 of a tomato plant, right, and only record 0.67 of an observation, so we have to bump it up to 148. So we would need N equal to 148. And that rule goes for the sample size calculation with sigma known, but also for one sample proportions. Good. Any questions about that one? So for degrees of freedom, you round down, but for your sample size calculation, you have to round up. Yeah, so it gets tricky because, yeah, your degrees of freedom, you have to round down because you can't assume that you have a larger sample than you actually do, right? But here, if you only went to 147, your margin of error would end up being a little bit bigger than 0.5. And so that's why you have to round up. It's this sample size game. Okay. On to the next one. Oh, is that question 5? Oh yeah, nice. I don't know how I feel about this question. It's all these rats. But anyways, so question 6. A study has linked consumption of caffeine in pubescent rats to a change in normal sleep patterns. We know that uncaffeinated rats have a normal sleep time distribution with a mean of 8 hours. Suppose a simple random sample of 27 caffeinated rats, yuck, produce the following results. So they're all a-buzzing, and they slept for an average of 7.25 hours with a standard deviation of 2.5 hours. Assume that the sample data doesn't have any skewness or prominent outliers. Perform a hypothesis test to determine whether the sleep time of caffeinated rats is less than the known sleep time of uncaffeinated rats. So what that's actually saying is it less than 8 hours, right? Because we know it's 8 hours. Clearly state the null and alternative hypothesis, find the p-value, and clearly state your conclusion using alpha equal to 0.05. One thing that I will say before I forget is for these means problems, right, the hypothesis testing and confidence interval for the means, what you'll notice in the solutions is that they've gone through and checked assumptions, but I'm the one marking your final, and I haven't emphasized assumptions for means questions, mostly because, well, we have to have a random sample, yeah, doy. We have to assume it follows a normal distribution. We're probably still going to do it if it doesn't, right? And so these assumptions are kind of fake assumptions. The assumptions that I need you to do is for the proportions, right? So those I'll be checking, but I've got a little note in there saying be sure to check the assumptions for proportions questions. So for means, if you're looking at the solutions, right, they're like this, I just printed them off. They're checking the conditions. That's not something that I want you to worry about. For the means questions. Proportions, yes. Okay. And so what do we have here? Again, we just have one sample of caffeinated rats, and we want to compare it to some value, the sample mean to some value. So for our type here, we've got one sample mean, sigma unknown, right? Because our standard deviation is just from the sample of caffeinated rats. No mention of a confidence interval, and it looks like, yeah, perform a hypothesis test. Right, and so we have to do a full-blown hypothesis test. Step 1, we have to state the hypotheses. Our null and alternative hypotheses. Our null hypothesis is going to be that mu is equal to 8, right? That's the value that we want to compare our sample mean to. And we want to know if it's less than the known sleep time, less than 8. So is mu less than, 8. Because we're only concerned about the one side, right? Is it less than? We've got a one-sided test. Okay. Step 2. I don't know. I feel like at this point, the hard part, that's all done, right? Figuring out what type of question you have and setting up your null and alternative hypotheses. After that, it's kind of smooth sailing, right? Work. You have to do your calculation, find your p-value, do your conclusion, but you can kind of go on autopilot here. So do the test. For one sample mean sigma unknown, we calculate t, right? T is x bar minus mu over s over root n, which in our case is going to be, let's get these numbers here, 7.25 minus our hypothesized mean of 8 over 2.5 divided by the square root of 27. (7.25 minus 8, negative 0.75 over 2.5 divided by the square root of 27 divided by 0.4811252224. It's going to be you guys after this class. Negative 1.558845727. T, remember, has to have 3 decimal places because the T table has 3 decimal places, right? So you're always trying to match the table. So negative 1.559. Step 3, find the p-value. Using the T table, if we're using the T table, we have to have degrees of freedom, right? With degrees of freedom equal to n minus 1. Our sample size is 27 minus 1 is 26. So we go to the table, and if we find 26, that's great. If not, then we have to round down, right? But we're going to have the 26 lines, so we're a-okay. So using the T table with 26 degrees of freedom, we find, and it's been a little while since we did t-scores, right? But we write our absolute value of t equal to our calculated t, negative 1.559, is between 2 values, right? So now we take our calculated t and we're trying to place it on the 26 degrees of freedom line. And we'll find that it'll fall somewhere between 1.315 and 1.706. Yeah, so the absolute value just says stitch the negative. So, and then again in the middle, I need a one-sided p-value, right? So, because we have a one-sided test, so our one-sided p-value. Now you scroll down to choose your one-sided or your two-sided. We decided we need a one-sided. And reading these from right to left are one-sided p-values between 0.05 and 0.10. All right, conclusion. Step 4 is your conclusion. So our one-sided p-value is somewhere between 0.05 and 0.1. Our alpha level, we were told to use 0.05. Right? This here is telling us that our p-value is larger than 0.05. Right? It's somewhere between 0.05 and 0.1. So it must be greater than 0.05. But we use the same kind of blurb. Since our one-sided p-value is between 0.05 and 0.10, it is not less than alpha equal to 0.05, which means we do not have enough evidence to reject H0. We do not have enough evidence to reject H0. Good luck with your presentation.
Bring attention to the fact that
No, we'll wait. Yeah. So our conclusion, therefore, well, what does that mean? It means that our caffeinated rats don't sleep any significantly different than 8 hours. And so how can I rephrase that? To determine whether the sleep time of caffeinated rats is less than the known sleep time of uncaffeinated rats, our conclusion is that no, there's no difference, right? And so the sleep time of caffeinated rats is not less. Therefore, the sleep time of caffeinated rats is not less than uncaffeinated rats. Good. Any questions about that one? So that one just had that one big question, no parts for that one. So I think we're on to the next one.
Would there ever be a situation where like P isn't between any numbers, like it's an exact number?
Oh, like it's one of the exact numbers? Then you could just use, so say your T for 26 degrees of freedom was 1.315, then I guess your one-sided p-value would be 0.1. So you could just use that. But no. The probability is very small. Get on to the next one. So question 7. We'll just read the question before I skip around. A factory hiring people to work on an assembly line randomly gives job applicants a test of manual agility. It doesn't really say what we're measuring, but who cares? Probably time or something. I think I have a very similar one where they have to place the number of pegs that you guys have gone through, right? But it's just two sample means hanging out, wanting to get compared. And so construct a 95% confidence interval for the difference between the population means of men and women. Again, not really clear what we're comparing, but that's okay. And then part B, is there a difference in manual agility based on the sex of the applicant? Use your 95% confidence interval to make your conclusion or to draw your conclusion. And so same idea, right? We're gonna use our confidence interval to test the hypothesis that they're the same. So copy. So for the type here, we've got a sample of males, a sample of females. We're given the means and the standard deviations of both groups, right? So now we have two, and then I'll put in brackets independent sample means. And so two independent, two sample means. I like to throw independent in there just to emphasize that these two groups have nothing to do with each other, right? The means are just being compared. So we have to make a 95% confidence interval. And so our formula in general is going to be x1 bar minus x2 bar plus minus t star times the square root of s1 squared over n1 plus s2 squared over n2. You want to be really careful that you're not forgetting any squares or the square root, right? So you want to take your time doing this calculation. If we let the males be group 1 and the females be group 2, just because that's how I read, bless you. We've got x1 bar, we've got s1 bar, or s1 bar, S1, N1, and then we have X2 bar, S2, and N2. So the only thing that we need is our T star, right? T star means we have to find our degrees of freedom. And so we need T star with degrees of freedom equal to, so for two sample means, our degrees of freedom is the minimum of N1 minus 1. Or N2 minus 1, essentially the smallest sample size minus 1. Our N1 is, oh, forgot the minimum. N1 is 45 minus 1, or 31 minus 1, which is the minimum of 44 or 30, which would spit out 30. We'll just check on our table, right, the T table, to see if we have a 30 degrees of freedom line, which we do. So then we're just going to use 30. T star is going to be, okay, so we've got 30 degrees of freedom, and we wanted a 95% confidence interval again. So 95, and then we stop at 30 degrees of freedom. So we find T star is 2.042 for a 95% confidence interval. So now we have everything that we need. So now we can just plug them in, see what we have. I'll rewrite the empty formula just so it's on the same page. X1 bar minus X2 bar plus minus T star times the square root of S1 squared over N1 plus S2 squared over N2. So then we're going to have x1 bar is 19.5 minus 17.25 plus minus t star, which is 2.042, times the square root of 2.5 squared over 45 plus 3.5 squared over 31. All right. 19.5 minus 17.25. We'll just have 2.25 hanging out on the left-hand side, and then 2.042. I'm going to simplify the 2.5 squared over 45. 2.5 squared divided by 45. 0.1388 repeating. I'll store that. And then 3.5 squared divided by 31. 0.39516,129 plus recall 1 plus minus 2.042, 2.25 on the left. We're going to have to take the square root of 0.534050179. Square root that. We've got 2.042 times 0.730787369. 2.25 plus minus times 2.042. 1.492267808. I'll store that because then I have to take 2.25 minus the margin of error, right? The margin of error is the 1.49. Puts me at 0.757732192 up to 2.25 plus the margin of error, 3.742267,808. I will round this. There's way too many to lug around. Let's go to, I don't know, 3 decimal places. So 0.758 up to 3.742. Now it's time to interpret this interval, right? So again, we are 95% confident the interval from 0.758 to 3.742 captures the question said, construct a 95% confidence interval for the difference between the population means of men and women. Still no mention, means of what? Nobody knows, it doesn't matter. But so now we're 95% confident that this interval captures the difference between the population means of men and women. So now we can move on to part B, which is really just asking, is there a difference between men and women? And so we've got this interval for the difference, right? The difference in the means. And so that's going to be mean 1 minus mean 2. So because this interval is all above 0, right, or 0 is not in this interval, right, that means that we can reject the null hypothesis. So I'll copy part B and we'll do it together. So is there a difference? Use the 95% confidence interval to draw your conclusion. And so our null hypothesis, right, if we've decided that we have two sample means that we're dealing with, our null hypothesis is going to be that mu m is equal to mu f, right? Using those question-specific subscripts, just so our comparisons make sense, right? You don't want to do the generic mu1 and mu2. You want to assign the groups. Our alternative hypothesis, we just want to know if there's a difference, which few, because our confidence interval only does the difference, a two-sided test. So we want to know if mu m is not equal to mu f. If mu m is equal to mu f, then mu m minus mu f would be 0. Since our confidence interval is consistently above 0, we have enough evidence to reject H naught in favor of HA. Therefore, there is a difference in manual agility I'll just say for men and women. So you take your hypothesized value, right, and see if it falls in the interval, then you can't reject the null hypothesis. But if the interval is off of that hypothesized value, right, then you can reject the null hypothesis. Any questions about that one? No. All right. So like I said, question 5, 6, and 7, right? Those were means questions. We happen to see one sample mean sigma known, sigma unknown, and two sample means. So there was no matched pairs in there, but there very well could have been, right? And so, and we saw a confidence interval hypothesis test and then a confidence interval again. So, and of course, those could have changed as well. So you'll want to have a look at the other practice tests, right, to get an idea of some other types. So now, question 8 and question 9, those are proportions questions, right? And so in a random sample of 520 judges, it was found that 286 are introverts. Weird thing to study, but okay. Let P represent the proportion of all judges who are introverts. So part A, find a 98% confidence interval for P. And then part B, suppose you want a margin of error of 0.04. Then we have to do a sample size calculation. One where we're assuming we have some preliminary data, so we use our sample, and two where we have to just use the conservative approach of a 50-50 split. Okay. So we'll go ahead and find our confidence interval. So here, first we'll talk about what type of question this is. Here, there's no mean, there's no standard deviation. So right away, you're starting to think, okay, this must be a proportion question, but then you see the word proportion, things are looking even more like a proportion question. And so we only have one sample, right, of 520 judges. And so this is a one sample proportion. So here's where I'm going to start emphasizing the assumptions, right? And so we have to check, okay, am I doing a confidence interval or a hypothesis test, right? Because my assumptions change a little bit depending on what I'm going to do. Here we're doing a confidence interval. And so for one sample proportion, for a confidence interval, we just have to make sure that we have at least 10 successes and 10 failures in our sample. Our assumptions. Well, the first assumption is that we have a random sample. It says in a random sample of 520 judges, so I'll just say that it was stated. The next thing we have to check is that n is less than 10%. Our n is 520, and it has to be, we have to assume that 520 judges is less than 10% of all judges in the world, I guess. I don't know, I guess. How many judges can there be? We're assuming there's a lot. So we assume, so the assumptions, even if you're not convinced, right, you still have to say, well, here's what I'm assuming. We assume n equal to 520 is less than 10% of all judges. That's something that we're about to assume here. For a confidence interval, we have to check that n times p hat, which is more simply x if you know it, right? Just the number of successes, which in our case is 286. It's more than 10, so it checks out. Then we have to check that nq hat, which is just n minus x, right? Your sample size minus the number of successes, which in our case is 234, is also greater than 10, so it checks out. Therefore, assumptions are met or something like that. You don't have to say that, but just to show you that that's it for the assumptions. I'm gonna go ahead and calculate P. P is the number of successes over N, which in our case is 286 over 520. 286 divided by 520 is 0.55. Q hat is 1 minus P hat, which in this case is 1 minus 0.55. So 0.4. We want to build a confidence interval, and just so I don't have to write out the interval twice, I know how lazy, I know I need Z star, is for a 98% confidence interval, 98%, Z star is 2.326. for a 98% confidence interval. So now I can build my interval here, p hat plus minus z star times the square root of p hat q hat over n. After you've checked your assumptions for proportions questions, I actually find that they're easier to deal with, right? Because there's actually less things that you have to keep track of. Right? Just give you 286 out of 520, and then you've got everything you need. So we've got 0.55 plus minus 2.326 times the square root of 0.55 times 0.45 divided by 520. .1236 times the square root of 0.123 zeros, and then 475962. Square root that. Keep my 0.55 on the left-hand side, and times 2.326, I get 0.0, make sure, yeah, 0.050745278. Store that. 0.55 minus your margin of error here is 0.0507, blah, blah, blah. So 0.055 or 0.55 minus the margin of error is 0.499254722 up to 0.55 plus the margin of error is 0.600745278. Or let's round it to 3 decimal places, 0.499 up to 0.601. We have to interpret this interval. Remember, we're talking about the proportion of judges who are introverts, right? And so now we are 98% confident the interval from 0.499 to 0.601 captures the proportion of all judges who are introverts. Question? Yeah. I know. How rude. Yeah, so p hat, you do have to know how to find it. But once you've got it, then you know. Once you got it, you got it. So one thing I wanted to say, right, was find a 98% confidence interval for P. So it doesn't actually say what for, but then let P represent the proportion of all judges who are introverts, right? And so it's just use that little shorthand. So that's how you know what P is, because they've told you. So let's do these sample size calculations. Remember, for proportions, we had 2 different options for calculating our sample sizes. So now we want a margin of error of 0.04. if you're using your sample proportion as preliminary data, what that's telling you is that, okay, well then P star is P hat. Right, so use P hat as your P star, so 0.55. Your sample size calculation is Z star over M, so it's squared times P star Q star. I'll just double check that. Yeah. We assume the same confidence level, right? So our Z star is still going to be 2.326 over M, which we're forcing to be 0.04. Square that, and then using 0.55, and 1 minus 0.55 is 0.45. 2.326 divided by 0.04, square that, times 0.55 times 0.45, I get 836.9020688. So we would need N equal to 837 judges. If we didn't have a sample already, right, then we're just going in blind and we're saying, okay, what sample size do we need? So that's what this next part is. So you have no estimate and use a more conservative approach, which is just assuming P star is 0.5 and Q star is 0.5, right? Assume that it's just a 50-50 split, and that will give you your biggest estimate for N that you can get. So then N is going to be Z star over M again squared times P star Q star. But what this is saying is, so you have no estimate, so P star is going to be 0.5 is what that's telling you. So we've got 2.326 divided by 0.04 again, squared. The only thing that's changing is your P star is 0.5, and then 1 minus 0.5 is still 0.5. 2.326 divided by 0.04, square that, times 0.5 times 0.5. So we get 845.355,625. So we would need N equal to 846 judges. Oh, it's just because as a fact, if you have no prior information, you're going to use 0.5. So that's the more conservative approach. Yeah. Yeah, so we just assume, okay, there's a 50-50 split here. We don't know anything about it. But also because 0.5 is going to give you the biggest estimate possible. Cool. Okay. So the 837 judges versus 846, why not go for 850 and call it a day? Okay. All right. Any other questions about that one? Let's see what we can do on the 2 sample proportion one. On the plus side, you did it on your assignment. So maybe because of that, should we do, oh, I was in there already. Do you guys want to do the 2 sample proportion or the regression one? The regression one? So 9, is just 2 sample proportion. You have to check the assumptions. The solutions are posted, so I'm not too worried about you guys, but you also did it. I stole it for your assignment, so you've seen it before. Skipping question number 9. Eek. You can go ahead and do A on your own for the regression question, but it's not something that you're going to have to do. Of course, you're all very able to find the mean of X and Y. We will. Oh, we'll need it. I'll give it to you. I'll just tell you what it is. 9 and 10. X bar is 23 and Y bar turns out to be 54.4. The correlation, right, is SXY over SX times SY, which is, so we're given SXY 282.5 divided by SX, which is 16.34, times SY, which is 20.42. times 20.42. 282.5 divided by 333.6628. 0.84666315.8. Rounding to 3 decimal places, 0.847. Why not? Positive, right? So it's telling us that we have a positive relationship, and because it's bigger than 0.5, then we have a strong positive relationship, assuming that it's linear, right? We'll go ahead and assume that we have a linear relationship. We'll just do part C. And like I said, for part D, because we won't have time, make a scatter plot and draw the regression line on it. You'll have to, I'll give you the scatter plot, but you have to draw the line, right? Which means predicting 2 values, plotting them on there, connecting the line. And then part E, use your regression equation to predict when the temperature is 25 degrees. First thing we have to do is find the slope. The slope is R times SY over SX. 0.847 times SY, which was 20.42. You have to be careful that you don't mess up your, or mix up your SY and SX. 16.34. Which is, I'll just steal it from here, 1.0581. Now we can find our slope, right? Because our whole goal was to find just the, what's the least squares regression line. So that means find the intercept, find the slope, plug them in. So B0 is Y bar minus B1 X bar. Y bar we pretended to find was 54.4. Minus 1.0581, which you just found, times X bar, which was 23, which I'll steal from here, is 30.0637. So your least squares regression line, Y hat is B0 plus B1X, which in our case, Y hat is 30.0637 0.37, not rounding, plus 1.0581 times x. So that's your least squares regression line. And now we got an extra minute together. It's been my pleasure. You guys have been a really fun group. And I guess I'll see you on Monday if I don't see you before then. But like I said, I'll be around if you have questions. So let me know. Otherwise, I'll see you on Monday.
What time on Monday again?
9.
So